Knowing how much heat is released or absorbed when phase changes occur can have important applications. For example, heating and air conditioning of a space relies heavily on the cycle of evaporation and condensation for a particular substance. To calculate how much heat is transferred in these phase changes, we first plot the change that's occurring. When we heat a substance, we plot its heating curve. The plot on the left shows heating of a solid beyond its melting point, and on the right, we see heating of a liquid past its boiling point. What we are plotting on the heating curve is the temperature of a substance as a function of the heat that's added to it. This plot shows a heating curve for a substance going through all the phases, solid, liquid, and gas, of the substance. Heat has a symbol Q. In heating, we have two processes that occur. One process is the phase change itself. Phase changes occur at a constant temperature. For solid changing to liquid, this temperature is called the melting point, and for liquid changing to gas, this temperature is the boiling point. During a phase change, all the heat that is transferred is used to change the molecular structure of substance to correspond to the specific phase. For example, on the left is a picture of solid and liquid states of a given substance. At its melting point, heat is added, but the heat doesn't change the temperature. Instead, the heat is used to convert the molecular arrangement of solid, shown on the left, to the molecular arrangement of liquid, which is shown on the right. Similarly, at the boiling point, the heat that is added is used to rearrange the molecule from its liquid state to its gas state. The key point here is that during either of these phase changes, the temperature stays constant. In the heating curve, the phase changes show up as horizontal lines. Heat is added, but the temperature stays constant. Point 1 here corresponds to the melting of the substance, while point 3 corresponds to the vaporization of the substance. As you can see from the length of these lines, it takes more to vaporize a substance than it is to melt it. The amount of heat needed or released can be calculated by multiplying the enthalpy of phase change with the amount of substance we have. Now, what about these other lines in the heating curve that have slopes into them? These correspond to heat added to the substance while it stays in the same phase. So for example, if you imagine taking water from the refrigerator to your kitchen countertop, the water stays liquid. It just goes from a colder or lower temperature to a warmer or higher temperature, but the phase doesn't change. In this process, the heat added is converted to faster movements of the molecule. The faster movement is reflected as the higher temperature. So in this case, the substance stays in the same phase, but its speed increases. The heat that you need for this process is calculated differently compared to the phase change heat. We use the following equation, where heat is Q, where heat, or Q, is equal to mass times specific heat of the substance times the change in temperature. Specific heat is the amount of heat needed to raise the temperature of a given mass of substance by 1 degree Celsius. Different substances have different specific heats, and it is a value that you can obtain in textbooks or reference books. The equation is written as Q equals m times C sub s times delta T, or we usually use the acronym Q equals MCAT to remember this equation. The total heat that's needed for the entire heating curve is just the sum of all the steps in the curve. We're going to work through an example of how to use the heating curve to help us calculate the amount of heat needed to go through a particular process of phase change as well as heating the substance to a certain temperature. This problem here says that you have to calculate the heat that's needed to convert 58.9 grams of ice at 0 degrees Celsius to water at 81 degrees Celsius. And then it gives you a couple of information, the heat of fusion of ice and the specific heat of water. So the first thing to think about is what's the process that's going to happen. So we have some blocks of ice at 0 Celsius, and what we're trying to get to is liquid water at 81 degrees Celsius. And so in our heating curve then, we have to plot which part is going to be needed to reach from the beginning beginning to the end. So heating curve has temperature as the y-axis and heat added as the x-axis. We start with ice at 0 Celsius. Now here you need to remember that 0 Celsius happens to be the melting point of ice. Therefore, at this point we're in the melting process. So that means that in terms of the heating curve, this is your 0 degrees Celsius. So you're going through this process of melting, and once all the ice is melted and becomes liquid water, then you're going to go from that 0 Celsius all the way to 81 degrees Celsius. Basically, we're looking at this process right here in the heating curve. So it's really this two part of the heating curve that we would need to calculate. The part where it's flat, which is the melting part, and the part that it's going up with a slope, and that's the part where the water is being heated. So that means there's two stages that we need to calculate. The melting, one is the heat needed to melt, and for that we just need to calculate using the enthalpy of that melting process, which is the heat diffusion, and it gives you 335 joules per gram of ice, and you just need to multiply that by how much ice you have, which is 58.9 grams, and that would give you 1.973 times 10 to the fourth joule. And then now you need to do the next step where your liquid water is at 0 degrees and you need to heat it all the way to 81 degrees Celsius. So heat needed to bring liquid water from 0 to 81 degrees Celsius. And for this, we're going to use our MCAT equation, MC delta T. The mass of water is 58.9 grams. The specific heat of water is given as 4.18 joules per gram degree Celsius. Delta T is the change in temperature. So the final temperature is 81 degrees Celsius. The initial temperature is 0. So that's your delta T. And you can see your units cancel out here, leaving you with just joules at the end. And that would be 1.994 times 10 to the fourth joule. So the total heat needed is just going to be the sum of those two numbers, which end up being 3.967 times 10 to the fourth joules, or how we report these numbers is usually in kilojoules. So that's just going to be 39.7 kilojoules if we have a 3 sig figs number.